Hello, everybody, and welcome to now our 35th Inspiration Exchange session. My name is Dr. Fergus Imrie, and for those who don't know me, I am a postdoc in the Schaar Lab, and I'm delighted to host these Inspiration Exchange sessions, which are also organized by Tennyson Liu and obviously Professor Mihaela van der Schaar. And I'm excited today to enter the second part of our two-part topic on large language models. Before going any further with the topic, I want to re-emphasize that we are still advertising for PhD positions within the Schaar Lab. So if you're interested in today's topic of large language models, or indeed any topic under the field of machine learning, and especially as it relates to healthcare, please do get in touch if you're interested. Positions are still available, but we really would like to hear from you as soon as possible if you are interested in joining us. In today's session, will consist of two parts. In the first part, we'll have two presentations from members of our lab on recent developments in large language models, and these will be from Hao Sun and Thomas Pouplin. In the second part of today's session, we'll then move to a roundtable and Q&A session with two wonderful guests from industry who I'll introduce more formally later on in today's session. As always, if you've got any questions for any of our presenters or panelists today, please post these in the Inspiration Exchange channel on Slack, and do so the earlier the better, and we'll try and get through as many of these later in the session. And we'll just post the link to join the Slack for any of you those who are not on it yet in the chat now. So now, without any further ado, I'd like to turn over to Hao for his presentation. Hao, when you're ready, share your screen and take us away.
I think it's working. Okay, thank you so much. Hi everyone, I'm Hao Sun from the Schaar Lab at the University of Cambridge. Today is my great pleasure to introduce our paper, Query-Dependent Prompt Evaluation and Optimization with Offline Inverse Reinforcement Learning. This is a joint work with Dr Vivek and Professor Mihaela van der Schaar. The great success achieved by large language models have made them an important assistant in our lives. To fully elicit the ability of language models, it is natural to consider the following question: how should we smartly interact with language models? For instance, when we want to ask a math question or a medical question, how to increase the probability of getting a correct answer from language models? Apparently, we can directly ask language model what is the answer of the math question or the medical question. Yet language model might struggle in reasoning for the correct answers because they are not trained to be mathematician or clinician. On the other hand, we may prompt the language model with some external, with some example questions and their corresponding answers. And then the language model can utilize their ability of in-context learning and improve their ability in answering those questions. The most famous few-shot prompting methods might be the chain of thought prompting, where we have group of examples of questions and the chain of thought of answering those questions correctly. Moreover, there are zero-shot prompting strategies. For instance, we can ask the language models to act as mathematicians or the clinicians to solve the problem. We can ask to solve our problems step by step, or we can ask it to take a deep breath. Researchers have found there are so many magical words that are quite useful for improving language models' reasoning ability of answering other questions. Finally, providing the language models with some external knowledge or database is another way of enhancing its performance in solving problems. For instance, if language models have access to online knowledge, like Wikipedia or knowledge from textbook, or some private database, the issue of hallucination of language models might be partially alleviated. In today's Inspiration Exchange, we will focus on the last two approaches. I will introduce our work using inverse IO to improve zero-shot prompting, and Thomas will introduce our work empowering language models with external knowledge. Let's first focus on the zero-shot prompting approach of enhancing language model performance. In zero-shot prompting, a query-agnostic prefix or suffix is added to queries. Some well-known zero-shot prompting strategies include the chain of thought that asks the language model to solve the problems step by step, and the interesting one from Google, the OPRO, that asks the language model to take a deep breath. However, no prompting strategy can be strictly better than the other. When we say the chain of thought prompting is better than not using any prompt, we say it's better on a distribution level or a population level. Therefore, how to effectively optimize the prompting strategy on a query-dependent level is still an open and important challenge. At a first glance, prompting can be formulated as an IO problem, where the prompting policy interacts with the language model and get feedback from the language model. Here, the language model is the environment, and the prompts generated by prompting policy or users are the actions. However, the application of conventional solvers of IO faces several challenges. First, when the language model is the environment IO, the cost of interacting with it can be extremely expensive, as IO could take millions of steps to converge. Second, the exploration is challenging due to the extremely high dimensional action space, which is the vocabulary space of natural language. Moreover, generalization in IO is hard. This is because most IO algorithms optimizes on a single environment, but we hope our prompting strategy can be generalized to unseen queries. So in our work, we propose to solve the prompt optimization problem using the inverse IO, which is also known as imitation learning. Before going to the technical details of our method, let's first have a fast recap of what are those concepts. So in IO, an agent interacts with an external environment to collect some feedback and updates its information on the current state. It's worth highlighting the environment is composed by both the dynamics model and the reward model. But sometimes defining reward can be hard. For instance, aligning language models or playing Go or chess, although it's quite simple to define winning the game to be the reward, but this is quite sparse signal for agent to really learn from. So in those settings, it would be very helpful to include human demonstrations in the learning process. A behavior policy in these cases can interact with the environment and generate a decision demonstration dataset, and then this dataset can be used in policy learning to learn efficiently from demonstrations rather than directly interact with the environment. Let us now go into the language model alignment task to better understand what are those concepts. So ideally, in language model alignment, this is an online IO setting where the language model as an agent provides a response to human queries, and human users are environment who provide feedback to those responses. However, such an online interaction could be intractably expensive, so that in practice, researchers use offline alignment dataset to containing different queries and preferred responses to line language models. In the vanilla IOHF approach, a reward model is first learned from the alignment dataset, and then this reward model is used to guide the optimization of the language model. In our work, we are not optimizing language models, but we are optimizing the way people or user asking questions. This is actually a special type of language model alignment. We can call it as an inverse alignment. To see this, in IOHF, we align language models' output according to human feedback. But in prompt optimization, we are aligning prompters' prompts according to language models' feedback. In IOHF, a reward model is learned from the alignment dataset and guide the optimization of language models. But in our work, we can also introduce a reward model that is trained with a prompting dataset and guide the optimization of prompting strategies. In practice, how should we find those demonstration datasets? We would first note the existence of rich human demonstration in prompting. When the prompt is proposed by different researchers or research groups, or generated by some experts or even some algorithms, we need to verify their effectiveness using open source dataset. We call such a process the evaluation of prompts. In such an evaluation process, different queries, prompts, and generated responses, and whether those generated responses are correct or not, can be collected as a byproduct. Those datasets already exist for example, arithmetic reasoning task where researchers have benchmarked different prompting choices. Otherwise, we can actually easily generate those datasets by interacting with the language models. In our work, with the great success achieved by our method, we call on the community to not only release their code in language model research, but also release their interactive chat logs with language models. And this offline dataset are important as demonstrations for prompting strategies to learn from. Our method works on such an offline dataset. We first build a reward model that takes the embeddings of different queries and prompts as input and try to predict whether their combination can lead to a correct answer or not. With such a reward model in the test time, for any given query, we are able to evaluate any given prompt for prompting strategies without access to the language model. And then we can select the best prompting strategy to use. We evaluate the proposed method on the arithmetic reasoning task using different language models at different scales. In general, prompting using offline inverse IO enhances the arithmetic reasoning ability, even when the offline demonstration is collected from only a single prompt. This is a very encouraging result because for many real-world applications, other than the math problems, we actually do not have a lot of prompting experience. Not surprisingly, we find having more prompting demonstration further improves the performance. And when rich human expert prompting knowledge is available, selecting the best prompting strategy out of those training ones and can already achieve good performance. Our method is significantly cheaper than the online methods, especially when the number of potential prompting strategies increases. It adds almost no extra computational burden when applied to language models running on local machines, and it costs less than $1 when optimizing query-dependent prompts for over 2,000 queries. The training of our method is also computationally efficient. People with laptop can run our code within 1 hour, and this can be further accelerated if you have a server. You can spend only 5 minutes to reproduce our main results. To sum up the takeaways of our work, first, it is effective and efficient to learn from a reward model with offline dataset and deploy this reward model for prompt evaluation and optimization in the test time. Second, as we have demonstrated in the experiments, reward modeling can be efficient and effective alternative to the language model-based self-critic method. Finally, offline dataset is an invaluable asset but neglected by the community previously. So please contribute to the field by releasing not only your code, but also your generated dataset when interacting with the language models in your research. Many thanks for your attention. Our code and offline dataset are released. And please also check our group GitHub repo for other amazing research projects. Thanks.
Okay. So my name is Thomas Pouplin, and I will present to you our paper, Retrieval-Augmented Thought Process as Sequential Decision Making. This paper has been the work of Hao Sun, Samuel Holt, Michaela van der Schaar, and myself, and it can be found on arXiv. So this paper started with the idea that yes, LLM in their current iterations are great and useful for many applications. However, as Hao said, they can still be greatly improved if we give them access to external knowledge. External knowledge means any database or collection of documents that the LLM could leverage at inference time. And so why external knowledge is so important? Well, first, it enhances the LLM in many ways. It allows him to recall information outside of its context windows, which can be beneficial for long multi-turn dialogues, for example. It also anchors the text generation into factual documents, hence reducing the likelihood of hallucination, which is of the most important in fields such as medicine or education. Finally, retraining a model is very costly, both in time and money. So how do we keep our models updated with the latest news? Well, using external knowledge is a cheap way, as you can just update the knowledge and not the LLM. More importantly, it also unlocks a new ability. The LLM can now work on private data. This data, which has been kept away from public disclosure and thus from LLM pre-training, is often crucial for companies and individuals. Thus, there are two ways for the LLM to access information. The main one is through training, which works for public data, mostly data available on the web. The second one is through information retrieval at inference time. This is mostly interesting for any data that could not have been seen the other way. This includes personal sensitive information such as medical records. This second way of integrating data can be done in a private environment through communication between your local instance of the LLM and your knowledge base. In this example, the private data are electronic medical notes. You need to imagine that hospitals have the database with hundreds of thousands of these records. Thus, it would be a tremendous help if each time they are healing a patient, they can just ask an LLM any questions about any patients, such as, should we increase the dosage of medication X for the patient with ID Y? And the LLM can fetch all the information required to answer the question. So what are the existing solutions regarding this issue? Currently, it's mostly RAG for Retrieval-Augmented Generation. As you can see in this diagram from OpenAI, this method is about submitting one query to an information retrieval model, which will return one document. Then this document is concatenated to the initial prompt and sent to the LLM. That's all. However, we and multiple other authors have noticed that the current RAG works poorly. It can even decrease the final performance of your model. Some reason for this lack of performance are that the model used to retrieve information are far from being perfect, which means that the LLM have to deal with irrelevant and noisy documents, and such documents are confusing them. It makes them wrongly answer when they have the correct answer in the first place. Finally, what if we need information from multiple documents? You remember the medical questions in the previous example? It needed to fetch multiple information. In RAG, this is constrained by the context window size. Knowing these issues, we have considered iterative prompting methods. This method resorts to multi-step reasoning by generating chunks of text called thoughts, and then using them to generate even more thoughts. By doing so, you end up generating graph of thoughts. We call this graph a thought process, and this is at the core of our method. Now we give an overview of our method. Its goal is to pair LLM with information retrieval. In particular, we are dealing with a question answering task. Thus, it starts in the green part with a question X. This question is used to initialize a thought process here, in which multiple documents would be inspected with regard to this question. These documents came from private data, as shown in part 3 in red of the overview. And in the end, the thought process outputs what we call the final thought, which is the optimal piece of information to answer the query X. Finally, the final thought is concatenated to the query in a prompt given to a frozen LLM Lout that outputs the answer. As you have probably understood, all the interesting operations happen in part 2. That is why we will zoom in on this part. As you can see, we have here the thought process in blue. In appearance, it's very similar to other prompting strategies. We iteratively generate thoughts. However, the novelty I highlighted by this slide is that on top of previous thoughts, new thoughts are also generated based on retrieved documents. Thus, by combining external documents and thoughts, we effectively ground our thought process into factual knowledge. In addition, we can query information from multiple documents, regardless of the context window size, and the iterative prompting helps filter out irrelevant and noisy information. Nonetheless, how are we building this thought process? How do we decide what thoughts and what documents we should pair together to generate a new thoughts? How do we go from the question to the answer? Well, one of the contributions of the paper is to recognize here a sequential decision-making problem. We model the thought process as a Markov decision process, MDP. And in this formalism, our state space is a space of thought process, which means the space of the graphs made of thoughts. An action is any combination of existing thoughts and documents. We name the thoughts phi. They are the nodes of the thought process graph. Thus, a new thought is generated by giving the combination of existing thoughts and documents described by an action to an LLM L-thought. Hence, the transition function P is known. The new state is the concatenation of the old state, the action, and the new thought. You can see the actions as the edges of the graph, if you want. If you remember it, the final guessed answer y hat is generated from the final thought. Therefore, the reward is only non-zero at the end of the process, where it is valued according to a function capital R that compares y hat and the true value y. Solving this MGP means optimizing the policy phi that selects the actions to maximize the reward function. And finally, the last major contribution of this paper is using Monte Carlo research to solve our MGP and de facto plan our thought process. I won't go too much into details as we are time constrained, but the two main information that I want you to remember is that MCTS is a tool to have a trade-off between exploration and exploitation. And this concept of exploitation is based on a scoring model. Each thought is scored. The more they help the LLM output the right answer, the higher their score. In the paper, we have tried 3 scoring systems. The first one is an oracle. When we know the right answer, we can use any thought as a final thought and compare the predicted answer with the right answer. However, this oracle isn't available at inference time, of course, thus we compare 2 different approximations. In the first one, we train a simple model to estimate the oracle scores of a future thought given its parents. In the second one, we leverage the reflection ability of the LLM by asking it to score its own thoughts. On the right, we have plotted the accuracy and the number of LLM queries for different thought process, size, and scoring systems. It showcases the main difference between the scoring system. The main takeaways are that the full line in green, the oracle's accuracy, keeps increasing with the size, but it takes time to reach 100% accuracy. The LLM sometimes needs lots of iterations to pivot to the right answer. On the other hand, the 2 other scoring systems, so the purple full line for self-critique here, and the blue full line for the estimation scoring system, they plateau after a few iterations. The interesting difference is in the dashed line, so here and here, because we can see that the estimation scoring system is much cheaper in LLM queries compared to the self-critique, as it doesn't query an LLM to obtain the score. We first present results on private knowledge. This is the most interesting experiment, and this is exactly the setting of the example we have seen earlier. Here, we use the EMR-QA dataset, which is a set of questions about patient medication. The answer to these questions can be found in electronic medical notes, which are our knowledge base. First, we want to give credit to the LLM that correctly guessed the right answer 38% of the time. It is truly a guess, as the LLM didn't have access to the medical records, which are required to answer the questions. The insight here is that the LLM usually outputs the most used or the default medication, which is often the correct one. Also, we can see here, as expected, RAG performs poorly. In contrast, our method performs exceptionally well with up to 50% improvement here for the MCTS with self-critique scoring system. The MCTS with the estimation scoring system has more difficulties. We hypothesize that the medical notes are a bit too complicated and unstructured to be dealt with effectively with the low complexity model we are using to approximate the score. However, we didn't stop here. And we try our method on open knowledge, which means public data that's seen by the LLM during the training phase. In particular, we are using the BullQ dataset, which is a general question answering dataset. We use Wikipedia as a knowledge base. For this experiment, the main takeaways are that we still observe a boost of performance provided by our methods. I need to emphasize that this boost of performance here is actually a surprise, as we are talking about knowledge seen during the training. It shows that LLMs have a bad memory, and that even in these settings, our method is still provide some benefits. And in these settings, where the documents are Wikipedia articles, so much more structured and simple to read, the scoring models have a similar performance, which makes the estimation scoring model very interesting as it required fewer LLM queries. To sum up, our method is an information retrieval and LLM pairing method that can work with private data, that can process documents beyond the context windows, that uses iterative prompting to increase the robustness to irrelevant information, and that is totally interpretable as every thought is transparent in natural language. We want to highlight that this method can have a broad impact by making LLM more accessible and personalized to any company or institution, and for a very cheap cost compared to LLM training. And of course, the paper can contain many more details. You can find the paper at this link. And thank you for listening.
Now I'm really excited to move to our panel discussion and to welcome our two guests. Our first guest is Dr. Chris Anagnostopoulos, who is a partner and director of life sciences innovation at QuantumBlack AI by McKinsey, and is also an honorary senior lecturer at Imperial College London. I'm also delighted to welcome Dr. Vivek Natarajan, who's a research scientist at Google Health AI. And for the purposes of this session, I'm super excited because he leads Google's efforts in MedPalm and MedPalm 2, Google's flagship Google's flagship large language model. I'd like to kick off the discussion today, perhaps discussing that very topic and this idea of more specialized large language models than just general purpose models, let's say, that we see in ChatGPT or Llama more generally. Maybe both of our panelists, some of their thoughts about what do you think are maybe some of the best strategies for about creating more specialized large language models, and the more focused on either a user or a field or a domain more generally, and ways of achieving this, and both now and maybe in the future. Don't know if Chris or Vivek, you want to jump in first?
Happy to get us started, and it's very exciting to be in this group. First, maybe taking a step back to introduce a little bit myself and my perspective, right, through all of this. I started off as a researcher and an academic, and then I moved to industry where I've spent the last, say, 10 years or so working on AI, in particular for life sciences applications, and most recently, in particular for biopharma R&D at QuantumBlack, which is the data science arm of McKinsey, the consulting company. And I think that, what we see from, just to offer a little bit of a perspective from the users, the downstream end users of these technologies, is that there's a huge amount of excitement. Every single pharmaceutical company right now, I can tell you, is trying these models that you're all working on. So the excitement is there, the investment to make this work is there. But at the same time, there are many questions that there's no clear answer right now from the ecosystem. At least there's no clear answer that we can articulate easily. And one of these questions is precisely what you mentioned, Fergus. It's, thinking about more bespoke and specialized domains like biology. Of course, there's bespoke LLMs that are trained on a part of on a relevant corpus, right? Palm and MedPalm, and I hope to hear about those from the real experts today. But at the same time, many pharmaco researchers are wondering, at which point how do I decide whether a general purpose LLM is better for one particular use case in biopharma than a sort of more bespoke, specialized one? And thinking forwards, like, how can I project forward? Like, what will happen? Will it be the case that eventually the LLMs that are trained on curated data sets of just biopharma corpora are going to outperform the general purpose ones? Or are we actually leveraging some knowledge about human reasoning that you can't get with just looking at a specific scientific corpus, right? So these are some open questions that I'm keen to hear, both the perspective of the researchers and Mihaela, and also my fellow panelists today, on how we should best think about them.
Thanks, Chris. I can jump in over here. And first of all, thank you so much again for inviting me. So our perspective on specialist versus generalist models is it's not like an either or, it's rather both. And so the way we like to think about this is, I mean, if you look at how we train doctors today, they do undergo rigorous practice, several years of specialized training, followed by residency, interacting with patients in the real world, interacting with fellow clinicians in the real world, right? And so there is this process where we send them to medical school to undergo rigorous training. And if we require any kind of medical advice, we, as a society, the common practice is to go towards someone who's licensed to practice medicine, who's knowledgeable, not to some otherwise knowledgeable chap that you might have access to, and many of our friends might be the same. And so it's what we are doing with respect to humans. But at the same time, we're not sending kids to medical school, right? We allow kids to go through like several years of education, through schooling, perhaps even undergraduate degrees, to build up like the base knowledge and reasoning. And then we send them to medical school. And so the way we think about generalist versus specialist models is kind of like similar. So when you train on large scale internet corpora, including say multimodal data, you build up an induced knowledge within the weights of the network and induced reasoning capabilities, general purpose. And so that allows you in some ways to build models that can then learn better when you give them specialized tasks. And so once you have a base general purpose model, and so the work that we do with, say, MedPalm or Amy or other LLM systems that we're building, we're not starting from scratch ever. We're always starting from a base model that has already undergone a lot of pre-training and training on internet scale data. But then what we are saying is a stage of, you can call that pre-training, you can call that fine-tuning, whatever you want, that's a terminology difference, but you need to then reinforce the medical knowledge in the models. And that can be something that is could have been part of the pre-training corpora, but more often than not, it is more specialized, it's more high quality, it is more curated. And once you put that back into the model again, then that really makes it stand out for biomedical applications. And so that helps us with the knowledge part of the model, but then there's also the behavior elements and how to interact in the real world and alignment with the values of biology and medicine, which are quite different from what you want to say in a general purpose chatbot like some of the Gemini models out there or GPT-4. So that comes from interaction in the real world and using things like reinforcement learning with human feedback and so on and so forth. But so just to maybe clarify, it's not an either or. You start from a base model, a generalist model, then you specialize it. And the specialization happens with higher and higher quality data and domain-specific data. And if your domain is valuable and important, you are more likely than not to have higher quality domain-specific data that will really help you shine out in a task compared to general purpose models. So yeah, hopefully that helps.
I really love that way of framing it. And if I can just follow up with a question. So, and maybe also inspired a little bit from Hao's research. It's definitely true. I can see why a general purpose LLM is required to just get you to basic toddler intelligence, let alone like, 18-year-old school graduate intelligence. I can definitely see that. And it's startling that we're able to do this now, right? Like, so yes, I see that. At the same time, some of the skills that a medical student needs to know by the time they enter medical school are actually more in the lines of formal types of reasoning that some of Hao's research, for example, is focusing on. Like arithmetic is one very basic example, but of course in chemistry and biology, there's different types of really formal types of reasoning you need to be able to do, like understanding the distinction between higher and lower orders in a hierarchy, understanding basic chemistry and kind of, maybe some specific maths applicable to that, units, right? Like units is a big thing. It's simple to us now, but like it's not simple to a 10-year-old and not simple to an LLM either. So I'm just wondering, is there therefore some third element we need to add, right? Like you need your general purpose intelligence, you need your bespoke ontology and domain knowledge, and then maybe you also need, depending on the application, to boost some of the reasoning abilities that are required for each task. I don't know whether that That's
I don't know, Chris, if you allow me to jump a little bit. So
Yeah,
a third component that was a little bit alluded to by Hao, and I hope he can say a few words, and also by Sam and Thomas, is potentially the need to learn from a corpus of examples that are somewhat personalized. So it could be that besides this advanced knowledge, it could be that, for instance, I'm a prostate cancer, let's say, specialist, and I see a set of patients that have certain characteristics, the type of queries that I'm interested in, and the type of literature and potentially clinical trials that I want to access to answer this are somewhat specialized. So what is possible in the work that Hao presented, and maybe Hao, I invite you to say a few words about that, is the fact that there is a possibility to have this third step of personalization to a particular clinic or specialty, where we can really learn how to adequately prompt these large language models, whether it is, let's say, stage 1 or stage 2, to really allow for more specialized answers and more carefully curated answers that are truly useful to the individual asking question, because you would like as fast as possible to get the best answer you want without wasting a lot of time on prompting. Or maybe whether a clinician that's maybe a junior clinician may ask a certain set of questions, but this additional instrument could suggest to you other questions that maybe you should be asking at this particular moment in time. How can you say a few words about that? Because your presentation was quite brief about how can we fine tune, for instance, to clinicians. Let's take the clinicians as example.
Yeah, sure. I think definitely we can bespoke our dataset or our method to any dataset or application scenarios. For instance, like in the prostate cancer dataset, we have lots of this dataset. We may have some clinicians have their expertise in diagnostics and maybe some other in this field. And they may use language models. They can interact with language models and generate an offline dataset when they interact with the language models, and those datasets can be used to train our reward model. So actually, there are two ways of improving language models' performance on a specific task. First, we can fine-tune the language model itself, which is a bit more costly than just trying to smartly prompt them or using the existing language models. So then the second approach is our method, where we don't fine-tune the language models, but we smartly ask questions according to our experience or from demonstrations from the expert queries, and whether those queries can lead to correct answers or not. So basically, I think with our approach, we demonstrate that with the learned reward model, we can actually build our method on top of any given dataset from any given expert language model interaction chat logs, and build a reward model and use this reward model in the future to smartly ask questions to the language models to make them stronger.
So in short, Chris, potentially what I propose is personalization to an individual or a group of individuals who have their own, let's say, operational scenario. And this doesn't need to be given to the outside world. It can be kept proprietary, which is something that we are very interested in. And the same thing happened in the work that Thomas presented, where the data that's used is not data necessarily that can be shared with the entire world, can be again kept private.
And
I don't know what you think about that.
This is fascinating. Just a brief question. Would you imagine this to be usable as a pre-populated list of prompts for formula for prompts, right? That can be used by a specific type of user group, like prostate cancer clinicians, or maybe a translator where the clinician asks a question in their own natural language, but there's a filter before you hit the LLM that translated to a more appropriate prompt. Is that those some of
both
the ways?
Both of them.
Yeah.
So they could be either a pre-curated data set that could help a particular set of clinicians. So it could be either a few experts that are selected from a certain clinic that are doing this pre-training stage, thereby empowering the prompting at the later stage by the entire community. But it could be even a few individuals who are satisfied or dissatisfied. We all know that we are trying to become better prompters, and we all discover that as we become better prompters, the results we are getting get better. And this is very targeted to us, to our needs, to our experiences and our knowledge and our rewards. And what I wanted to highlight, because that may not be very clear in the work that how I presented, this is what in this prompt IRL, this is becoming possible. We are highlighting it with tasks that are curated by others in the area of question answering in math, but could be almost anything. So from that point of view, this is an open source package, if you like, that I really hope that the world can use to further provide their data sets and specialize this prompt IRL for their own inner use.
Vivek, I don't know if you wanted to add anything onto that, onto some of those points.
Yeah, I think I broadly agree with what both Mihaela and Chris were saying over here, as well as how we also like to think about data in very similar, using very similar analogies. So if you think about it, there's like maybe 3 scopes over here for data. So the first one is broadly, that is everything that's in the public domain on the open internet. And so that's the first stage in which you train these systems and, make them as general purpose as possible. But then when you think about using them in the real world, you're probably going to have it either directly to businesses or enterprises and things like that, or maybe directly to people. And so when you put them directly to, say, the enterprises, then there's a business context that comes in. And so in the context of healthcare, that could be something like when a hospital is making some sort of a clinical decision, they have a big set of guidelines that they use internally that's shared by all the clinical staff internally. And so when a model is coming up with recommendations or responses or answering questions, it should be able to reference to that guideline or the huge set of internal documentation that a hospital system might have. But again, this is very specific to that hospital system. It can't be shared along with other enterprises or other hospitals. So you need to ensure that you're retrieving that information only at the time of deployment in that setting. But then further beyond that enterprise scope is, for example, a clinician is interacting with a patient within the confines of the system. And over there, you would bring in very specific data, such as the health record of the patient, to be able to, again, guide the interaction further and assist both the clinician and the patient. And so that's even one step of scope or context further. And that's the personalized context that I think both Hao and Thomas and Mihaela were all talking about. And so there are all these 3 scopes, and we need to build out the right tools to be able to do these kind of things. And I think with the combination of retrieval-augmented LLMs with all these long context models that are coming in, I think we're getting better and better at being able to solve some of these problems and challenges, but it's not perfect yet. The other thing I would maybe just very quickly add on is one of the things that I am seeing over the last 2 years working with LLMs is they're actually getting better at instruction following. So the need for us to come up with very complicated prompts is also gradually decreasing, because I remember 2 years back when I was first playing around with these systems, to get them to do anything useful, I would have to literally tear my hair apart. But now it's like I just tell them something and they're able to understand my intent so much better. They become so much smarter. So the need to come up with craft specialized prompts is, I would say, decreasing quite a bit. But then again, what we have is more like the Constitution AI kind of things, where you give broad guardrails, broad roles and responsibilities. And what we are seeing is, again, these models are becoming really, really intelligent now. So when you give them such a specification document and saying, this is the confines in which you're going to act, this is the guardrails, they're able to follow it pretty accurately. So it's quite exciting, but also a little scary at the same time, looking at the progress of it.
Thank you so much. I think I definitely agree with a lot of what you said there. And I think it's a really interesting point around prompting, and I think something potentially very important, especially as we get to quite specialist or users such as doctors. I know as kind of maybe computer scientists, we almost quite like kind of prompt hacking, to use that kind of a word, but I'm not sure how much let's say a doctor or a patient as an end user would appreciate something like that. So I wonder how much you think that will continue to improve. You mentioned you've seen a big improvement in the last 2 years. Do you think these models will just keep kind of getting better and better naturally from that point of view? Or do you think we will need more of, let's say, these kind of prompt translation models, or LLMs adapting to the specific user to almost understand for that user itself what they mean by their prompt via kind of further training? Do we think you'll see more of those things, or do we just think kind of scaling up and as we improve the underlying technology, this will almost just completely disappear?
Yeah, again, I don't like to say it's only one or the other. It's always both. So again, like the data that we have, trained these systems on, we probably exhausted like text data on the internet, but then there's so much vast multimodal data, and we're still very, very early in that in terms of figuring out how to train on that data, how to induce interesting knowledge from multimodal data, and that includes biology as well. And if you look at the amount of data that is being generated in biology, that's like probably trending up even faster than Moore's law. So in that sense, I would not say any of these techniques are hitting a wall anytime soon. I think we have the core algorithms to be able to learn from the data. We have the compute. And so there's going to be a lot of work in terms of scaling the systems up to the next level in the next few years. And with that, there's going to be interesting capabilities that emerge. But at the same time, the current set of models that we have, they are very, very competent, but they also have limitations. But one of the things is I think there's a lot of value still to be accrued in the application layer. And that is where, this notion of compound AI systems that I believe a few researchers at Berkeley and Stanford also recently introduced, but it's been around for a long period of time. And I think Stanford really likes to put a name to everything, like they did the same with foundation models, and now they have this. But it's actually a good idea. It's the fact that, it's not like you don't have to treat an LLM as just one-shot oracle. You can engineer complex systems by putting together a chain and sequence or a graph of LLM calls with different contexts, with different data, with iterative loops and so on and so forth. And doing that engineering is still, I would say, a lot of like domain-specific details are needed, like insights from clinicians are needed if you're working in the medical domain or with biologists and scientists. And so I think there's still a lot of value in that. And again, a lot of it can also be learned. So if you think about the graph that you're building, you can think about like evolution approaches using genetic algorithms. And if you have a good fitness function, then you can evolve and learn that graph and make it really, really optimal for the underlying scoring function that you're trying to optimize for, and so on and so forth. And so still a lot of value to be accrued over there, and a lot of interesting work to be done. So I feel like there's going to be, the people who are building the core foundation models, they're going to keep pushing up scaling, but also add in like new interesting insights, such as the long context breakthroughs that have happened recently, and also on the alignment side of things that Anthropic has done. But then with the current generation of models, with the GPT-4 class of models, you're still going to have like a lot of these application layer work that's being done with building compound AI systems to make sure that these things are of a lot of value to both enterprises as well as people at scale. And so it's a mix of both that's happening.
Yeah.
Well, thank you so much for that, Chris. Do you have any thoughts on that, maybe especially with your kind of QuantumBlack McKinsey hat on, about how
to pile on? Yeah, thank you, Fergus. So I think I completely agree with what was just said. Like what we see in deployments of Gen AI systems, and we've done hundreds and hundreds in the last year. Some of them were pure pilots, others have reached production by now. And what we do see is that almost always the answer is an engineered system. One aspect of accuracy, by the way, which is a slightly different lens on the same problems, is safety. And the reason why I say it's a different lens is because it's almost like a worst case scenario accuracy metric, right? Like you want to avoid really big errors in certain situations. So it's not the same as an average kind of metric. And there, generally speaking, what we see for now being the preferred solution is to have guardrails that leverage other types of systems. So for example, in life sciences, we often have queries to more traditional knowledge graphs that are kind of structured ways of capturing unstructured information, through in a relational database or even in a graph database, and just using that to almost sense check the answers or contain the answers of an LLM, and creating some metrics around, to what extent there's dissonance or consonance between these two sources of information. So definitely we see engineering larger systems, both in order to add additional value, but also to safeguard against hallucinations or other aspects of unsafe performance. One thing I did want to raise, though, before we go into Q&A, is that within this exact philosophy of engineering systems leveraging Gen AI, what we see a lot in biology is the use of foundation models rather than prompting as a module within these systems, right? So taking an embedding of a word, an embedding of a disease, an embedding of a drug that you extract from an LLM or an LLM-like model, to then embed it to enrich patient-level data, to enrich other sources of data, and even sometimes deployed within a classic ML workflows. For example, embedding a molecule through a chemistry foundation model, and then training a classical machine learning model to optimize for one of the properties of these molecules, right? So the question I wanted to maybe, from that observation, go back to all of you with is, do we feel that the progress that is now focused because of the huge consumer interest in LLMs, is it the same direction to improve the accuracy of LLMs when they're prompted with a question, than to improve the signal to noise ratio of the underlying foundation models and embeddings? Or are we really talking about two different research directions that are starting to diverge?
I will let Vivek answer first, because I think I'll be keen to hear his answer before I tell you what I think.
Yeah, I think it's a great question. So I think we're getting to this stage. I don't think it's too different in terms of the kind of work that we are doing. Again, if you divide it into different phases of like building some of the LLMs that are out there in the industry, the first phase that happens, which is the pre-training phase that we like to call it, it's very much analogous to learning good representations of the world. So over there, the goal is not really to optimize for one specific task or one specific use case or one specific modality or whatever, but rather throw in a bunch of data and let's make the model learn good representations of it and figure out similarities and relationships between different kinds of data at scale. And so at that stage, there's no real optimization that's happening. And so so the fact that we're doing that, and that is where I would say probably even like 90% of the compute today is spent. And when I say 90% of the compute, you can imagine how much of money or how much of flops and everything that go in over there. And I feel like if I were to look at it from that lens, I feel like it's not too divergent. What we haven't maybe done yet, or what maybe people haven't talked about more broadly, is how specific modalities of data, like learning representations of molecules or drugs and all those things, are happening beyond what we talk about with language and images and videos to a certain extent. But I can say for sure that that is all happening, it's just that people haven't broadly talked about it for different reasons. And so my view is it's not too divergent, because the approach that we are here taking is not like, we want to go directly towards the end goal or the end, end user optimization, or that whatever we are trying to do. But rather we are saying, let's first build up good representations of the world. Let's first build up models that have, good models of the world, if you would like to call it that way, although I think a lot of people will disagree with me if I use that word. And then we can, do the subsequent stages of post-training and alignment and safety to optimize for real-world use case and really provide value to users at scale. So that's my take at this point of time, but feel free to disagree or yeah.
Thank you, Vivek. So, Chris, my view is slightly different. I think that while definitely this whole effort on pre-training is a useful one, I am also quite excited about other ways of thinking. For instance, just very recently in our own lab with a very beginning but brilliant PhD student, Kasia, we started to look at how humans and machines can learn together and from each other. And we started to look at what we call informed meta-learning, which is a paper that we put in the archive relatively recently, where everything from teaching complex math to teaching about molecules to teaching about safety from a human perspective becomes possible. And I'm very excited about this parallel thread. This is not going against what Vivek said. It's just saying that I'm, as an academic who cannot pre-train these models and don't have the computational resources to do so, we in our lab are very excited about these new fields where, again, humans and machines are interacting with each other. On one hand, to learn things that potentially you cannot learn by just feeding more data, but rather you can feed by reasoning, human reasoning, and how that can be instilled in large language models, and vice versa, how large language models can empower this reasoning. So I want to give a shout out to my student Kasia, and maybe in a future inspiration exchange, we can have her and others in the group that think about this parallel way of thinking and invite the two of you to come back. Fergus, I'm aware of the time and the Q&A, so.
Definitely. No, thanks, Mihaela, and thank you, Chris and Vivek. That was a super interesting discussion and lots for me to think about, definitely there as well, and I'm sure for all of our audience. In what time we've got, I do want to take at least one question from the audience. I think Hyun Lee had a question for Hao. Hi, Hao. As I understand it, your research focuses on improving prompts through the use of a reward model utilizing Q&A datasets. Is it easy to utilize this approach in fields beyond just medicine and mathematics?
Yeah, thanks for the question. And I think our general framework is can be applied to general application scenarios, not limited to the math QA or medical dataset. I think the key takeaway is, first, it is way much easier in training a prompting agent than training a language model itself to perform better on a specific task. This is utilizing the in-context learning ability of language models, as also discussed by Kia in our Slack discussion. And the second takeaway is such a reward model is always learnable. We can learn this reward model from a limited number of offline dataset. So the answer is yes, we can apply this to general tasks, not limited to math QA and medical dataset. Thanks.
So just before we leave, I'd just like to remind everyone again that the lab is still looking for PhD students to start this coming academic year. So please do get in touch as soon as possible if you are still interested in this, if you're inspired by any of the discussions of large language models today, or indeed any of the other topics within a wide variety of machine learning subfields that are interesting to you. Today's session will be on YouTube soon, so if you have colleagues, friends that you think would really enjoy the presentations and discussion today, you'll be able to send that their way shortly. And our next session will be on the 17th of April, in just over a month, and we'll be covering rethinking ML interpretability, as well as giving a quick preview of some of our work coming up at ICLR. Thank you, everybody, for joining, and thanks again to both of our presenters and our panelists, Chris and Vivek, for joining us today. Really appreciate you taking the time to join this Inspiration Exchange session, and I hope to see everybody soon. Thank you very much.